Turn to page 465, Similar Polygons. We do have 3 learning targets in this section. We're going to use proportions, which are part of the definition of similar polygons, to identify similar polygons. We're going to solve problems using properties of similar polygons, and we're going to use the relationship between the perimeters of similar figures to solve problems. So first, we need to know how proportions come into the definition of similar polygons. So on page 465, we have this definition. We first have an informal definition. Similar polygons have the same shape, but not necessarily the same size. Now, they can have the same size, and we've studied polygons like that. We called them congruent, didn't we? When they have the same shape and the same size, they're congruent polygons. So, congruent polygons are a special case of similar polygons. So, we've already done congruent. Now, most of the ones we're going to do will have different size. They're the same shape, but probably different size. So, look at these 2 figures here. Same shape, but different size. So they're similar. Okay? Now, the formal definition. 2 polygons are similar if and only if their corresponding angles are congruent. So look at these 2 figures I just pointed out and said were similar. Angle A is congruent to angle W. Angle B is congruent to angle X. Angle C is congruent to angle Y. Angle D is congruent to angle Z. So, corresponding angles are congruent, and corresponding side lengths are proportional. Corresponding sides don't have to be congruent. Corresponding sides have to be proportional. And what does proportional mean? Equal ratios. So in other words, you make a ratio out of each pair of corresponding sides, and all of those ratios are equivalent to each other. Okay? So that's our definition, and that's how proportions come into this. Okay? So, looking at this example, if we make a ratio out of each pair of corresponding sides, I can make a ratio out of 15 and 5, then a ratio out of 12 and 4, and of 21 and 7, and of 18 and 6. Do you see how I got all those? Because that side corresponds to that one. That side corresponds to that one. That one with that one. And then that one with that one. So I made a ratio out of each pair of corresponding sides. What do all of those reduce to? They all equal 3 over 1 or 3, don't they? So all of the ratios are equal. That's proportional. When all of the ratios are equal, that means proportional. All right, so how would we use that? Well, one thing that's going to help. When we were writing congruence statements, the order mattered, didn't it? The order matters now. It tells us how everything corresponds. So as with congruence statements, the order of vertices in a similarity statement, like A, B, C, D, is similar to. So look at that. That little symbol right there means similar to. W, X, Y, Z is important. It identifies the corresponding angles and sides. So if we're told triangle FGH is similar to triangle JKL, we can list all the pairs of corresponding parts. Okay? Angle F is first, so it corresponds to angle J. So they're congruent angles. Angle G is second, so it corresponds to angle K. They're another pair of congruent angles. H is last. It corresponds to L, which is last. So that's your third pair of corresponding angles that are congruent. And then we can get the sides the same way. The first segment listed is FG, JK, so they correspond. Then the next side listed is GH, KL. Those two sides correspond. Then FH must correspond to JL. And remember, corresponding sides are not congruent. corresponding sides are proportional. Okay? Let's see if we can do that. This is part of your assignment from page 468. We're supposed to list all pairs of congruent angles and write a proportion that relates the corresponding sides for each pair of similar polygons. All right, now, leave a space for number 1 or just do number 2 before you do number 1. And I don't care. Let's do number 2 together because it's got 4 vertices instead of 3. I'll let you do number 1 by yourself in just a second. So, according to the way this is written, since J is the first angle listed in the first polygon and T is the first angle listed in the second one, they're a pair of corresponding angles, aren't they? And in similar polygons, corresponding angles are congruent. So our first pair of corresponding angles that are congruent is angle J is congruent to angle T. What's angle K congruent to? Angle S. Angle L is congruent to angle R. Angle M is congruent to angle Q. Did I even need to see the figures to know that? In fact, I didn't even look at them. I didn't. I don't need to look at them to get the corresponding sides equal, or corresponding sides either. So, JK corresponds to what? TS. So the length of JK, that's the length of that side, corresponds. The sides correspond, the lengths make the ratios. That's what I was trying to say. The sides correspond, the lengths make the ratios. Now, that's got to be equal to the ratio we make from every other pair of corresponding sides. Well, what is the next pair of corresponding sides? Well, how about KL and KL SR? What does LM correspond to? RQ. And what have I not listed yet? JM to TQ. So, the sides correspond, the lengths make the ratios. So that makes sense to you? All right, do number 1. And then check your work. See if you got what I got. Did you? Any questions? Okay. Back on page 466, the ratio of the lengths of the corresponding sides of 2 similar polygons is called the scale factor. Okay? Now, usually the scale factor is written in simplified form. For instance, if your scale factor was 20 to 30, you would simplify that down to 2 to 3. Okay? You don't necessarily have to, but it's accepted form to write it in simplified form. So the ratio of the lengths of the corresponding sides of two similar polygons is called the scale factor. Now the scale factor depends on the order of comparison. Here's what they're talking about. In this diagram, that's our similarity statement. That's what that's called, a similarity statement. Triangle ABC is similar to triangle XYZ. If I want to compare it this way, if I want it to be the scale factor of triangle ABC to triangle XYZ, which everything's listed first, that's the numerator of our ratio, isn't it? So look, doesn't that length of 6, because that's side A, look, well, let's do it this way. Doesn't side AB correspond to side XY? So the length of AB, if that's the triangle I need to put first, the length of AB is your numerator, leaving the length of BC, or of XY, excuse me, to be your denominator. So the scale factor is 6 to 3, or 2, because 6 to 3 simplified is 2. But then look, it all changes if they want us to write the scale factor of triangle XYZ to triangle ABC. Now we've got to put the side from triangle XYZ as our numerator. So the 3 becomes our numerator, the 6 becomes our denominator, and the scale factor is 1 to 2. If you're writing it yourself, it doesn't really matter. You write down your similarity statement, and then you write down your scale factor. But if they tell you the order to write it in, then you've got to write it in that order. You understand? Do you see why it matters? Because 2 and 1/2 are not the same thing, are they? So it really does matter which one you do first. All right, let's use this. Determine whether each pair of figures is similar. If so, write the similarity statement and the scale factor. If not, explain your reasoning. So if you recall, for number 3 here, there are 2 parts to our definition of similar polygons. 1, corresponding angles are congruent. Well, look at number 3. Aren't all of those angles right angles? So no matter what corresponds to what, we do have all the corresponding angles congruent, don't we? Because it's always going to be 90 congruent to 90. It's going to be a right angle congruent to a right angle, no matter how we match it up. But then, corresponding sides have to be proportional. So, how do we know which sides correspond when they don't give us the similarity statement? It works this way. Wouldn't the longest side have to correspond to the longest side? And wouldn't the shortest side of one of them have to correspond to the shortest side of the other one? So, doesn't 10, since it's the longest side of that one, have to correspond to 18? Make that ratio. And then doesn't 4, the shortest side, have to correspond to 9, the shortest side? Are those ratios equal? They're not. Okay? If I reduce 10/18, I don't get 4/9, I get 5/9. Another way to see if they're equal is to do cross products. Because if they're equal, the cross products will be equal. So if I multiply 10 times 9, I get 90. But if I multiply 18 times 4, I don't get 90. So they're not equal. The ratios are not equal. So, what do we say? We say not similar because corresponding sides are not proportional. All right, so we go over here to number 4. And maybe we can do better with number 4. Maybe we'll get similar figures. All right, first, let's see if we have corresponding angles congruent. I see a 36-degree angle here. Do I have a 36-degree angle in the other one? So there's one pair of corresponding angles that are congruent. In fact, I'm going to write a similarity statement. Well, I'll do it in a minute. And then I've got a 27-degree angle. Does it match up with another 27-degree angle? Yep. What am I left with? 117 corresponds to 117. All right, so we've got corresponding angles congruent. Now we need to see if corresponding sides are proportional. All right, we can either go in an order, either do the smallest sides first and go up, or do the largest sides first and go down. I don't care which, but just pick one and stay with it. So do you want to do smallest first or largest first? Largest, okay. So the largest side here is 12. So it has to correspond to the 6 because that's the largest side over there. What's that reduced to? 2. So let's see if the next one does. 8 would be the next largest. So what's it correspond to? 4. What's that simplify to equal? 2. So far, so good. Then 6 has to correspond to 3. What's that equal? So they are equal. Because they all equal 2. All right, so what are we supposed to write? So we've determined it. So, yes, they are similar. All right, good. We only have to explain our reasoning if the answer is no. All right, then we have to write a similarity statement. So, this one over here, let's just name it something. It would make sense to name it ABC, wouldn't it? Triangle ABC is similar to triangle. Yeah, and then we just match them up. A corresponds to H. And then B was what I wrote next. It's 27, so it corresponds to F. J must be last. Now, is that the only correct similarity statement? No, but if I switch this one around, like for instance, if I called it triangle BCA, then I'd have to call the other one, let's see, FJH, wouldn't I? So you can do that. That's not incorrect. Just make sure you match up the corresponding parts. And I've still got to list the scale factor. We've already figured it out. Now, for some reason, the letter K usually stands for scale factor, but we'll use that. So the scale factor is 2. If it's not a K, it's usually an R. You know? So we'll just call it K for now for the scale factor. So you think you can do problems like that? I think you can too. All right, solve problems using the properties of similar polygons. How are we going to do that? We'll look at this example real quick, and then we'll do some of our assignment. All right, so look what we're given. We're given a pair of polygons. That means corresponding angles are congruent and corresponding sides are proportional. And then look what we've got. We've got a variable in there. Okay? Now, in fact, we've got a variable in there as well. So in the example I copied down, we're just doing the x. Let's just do the x. So how would we go about finding this? Well, we need to find one pair of corresponding sides where we know both lengths. Or, well, I'll come back to the or. If we can find one pair of corresponding sides where we know both lengths, we can figure out the scale factor, can't we? Okay? So look here. All right, let's see. AC corresponds to VW. I don't know AC. I don't know VW. That's not the pair I want. CD and WY. 9 and 6. Good. So you make a ratio out of those. And then what does the side that you're looking for, what does the x correspond to? Well, look, x is the length of DF, right? So doesn't it correspond to YZ? So x corresponds to 10. And I get that ratio. Since they told us these are similar polygons, we know those ratios have to be equal. And then you do what we did in the last section, cross multiply and solve for x. Make sense? All right, now, I started to say you have to find a pair of corresponding sides where you know both lengths, or they all have the same variable involved. Okay, so for instance, if that had been 9x, 6x, and then x and 10, I could have made a ratio out of that. I just would have had x's in my problem, and I can solve that. So that you don't necessarily have to know an actual number for all the lengths. You just have to make sure you get just one variable in your proportion. It can be in there more than one time, but in other words, don't get an x and a y in the same proportion. We don't know how to solve an equation with two different variables in it. Okay? So as long as you're able to get a proportion that just has one variable in it, you're in good shape. We should be able to figure that out. All right, let's see. That's what we just did. So number 5 on page 468. Actually, we're on 469 now. They tell us in the directions. Each pair of polygons is similar. Find the value of x. All right, so we know they're similar. We don't have to wonder about it. So for number 5, what's one pair of corresponding sides? You can just give me the length. All right, 8 and 4. What's the other pair of corresponding sides? Okay, it's x and 3. I'm going to do this. All right, I will not get the right answer. Because what I've done is I've mixed and matched. I need to pick. When I wrote 8 to 4, I picked, whether I meant to or not, I picked the sides of that one to be numerators, didn't I? I've got to stick with that. Does that make sense? So whether you mean to pick or not, you're picking. When you make your first ratio, you've decided which figure becomes numerators and which figure becomes denominators. So there's nothing wrong with 8 to 4. But if I'm going to write that as 8 to 4, what did I better write that other ratio as? X to 3. Make sense? All right, let's do cross products. We get 4x equals 24. So x equals 6. Yeah, on that one's, if you think about it, sort of obvious, isn't it? 8's twice as big as 4, so shouldn't 6 be twice as big as 3? But they're not all going to be, and that, it still may not be obvious even once I pointed it out, but they're not all going to be obvious. Okay? Question? Yeah, that's a good question. All right. Look, the way I wrote that proportion down is not the only correct way. I could have, for one thing, written the 4 over the 8 and then the 3 over the x. I could even do this. I could put the 3 over the 4. So look what I did. I did short side to long side equals, then I got to go short side to long side. Now, I don't recommend doing that because if they're not similar, you'll never notice it. Okay? But there's always more than one proportion that works. Because as long as you're getting that with your cross products, you're going to get, it's the same proportion really, isn't it? So there are several different versions that you could write down. And I'm not going to show you all of them. But yeah, so there is more than one way to do it. But what I want to do and what I'm going to do is I'm going to stick with making the ratios out of the similar sides. Because, like I said, if it's not similar, we're just not the same scale factor when you write your ratio. Okay? All right, number 6. Now, there's a little bit more work here in number 6 because they give us more side lengths to work with. All right, so let's say that I'm going to do this one as my numerator. Well, how do you think this works out? What corresponds to what? If I do 20 to something as my first ratio, is it 20 to 5, 20 to 2, 20 to 4, 20 to 3? Okay. If I do 12 next, it's 12 to, and if I do 8 next, it's 8 to, and so if I do x next, it would be 8 to, or x to, how do I know if I've got, how do I know? What's that one simplify to equal? 4 over 1. What's that one to simplify to equal? That one. So I've got those 3 right, don't I? Because they all equal each other. So if that's the way it goes, then that's got to be the way I write the last ratio. So you follow me? You better make sure you got it right, right? If I accidentally matched up the 20 with the 3, am I going to get the right answer when I set up my proportion? No. All right, so here's the thing I want you to notice. Every one of those reduced down to equal 4 to 1. So when I make my proportion, how about just using 4 to 1? I can use any one of those 3. I can. But since I've already figured out to make sure I had them written correctly that they all equal 4 to 1, might as well use 4 to 1, hadn't you? What does x equal? 16. All right, last learning target. Use the relationship between the perimeters of similar figures to solve problems. If 2 polygons are similar, then their perimeters are proportional to the scale factor between them. I write it this way. For similar polygons, the ratio of the perimeters equals the scale factor. So whatever the scale factor is, like for instance, in this one, the scale factor was 4 to 1. That's what the ratio of the perimeters equals, 4 to 1. In this one, it was 8 to 4, or 2 to 1. That's what the ratio of the perimeters would equal, 8 to 4, or 2 to 1. The ratio of the perimeters equals the scale factor. I think we'll skip that. Let's do number 7. On the blueprint of the apartment shown, the balcony measures 1 inch wide, right there, by 1.7 inches long, right there. If the actual length of the balcony is 7 feet, what is the perimeter of the balcony? All right, now let's stop and think here. The length of 7 feet, does that correspond to the 1 inch or the 1.75 inches? The 1.75, that's the length, isn't it? Okay, how do I know? Because they said wide there and they said long there. Okay, so 1.75 inches corresponds to 7 feet. That's the scale factor. Now, it's not simplified. Heck, it's not even in the same unit. But that can be my scale factor. Okay? The ratio of the perimeters equals scale factor. I don't know what the perimeter of the balcony is. So I'm going to call it x. Why did I put x on the denominator instead of the numerator? Because it's the actual balcony, and that's what the 7 feet was, the actual balcony. Okay? Now, what's the perimeter on the blueprint? Wouldn't it be 1 plus 1 plus 1.75 plus 1.75? Right? 1 plus 1 is 2. 1.75 plus 1.75 is 3.5. 2 plus 3.5. So, 5.5 inches to x feet. That's the scale factor. That's the ratio of the perimeters. The ratio of the perimeters equals the scale factor. With me? That's a little iffier, isn't it? Okay? The ratio of the perimeters equals the scale factor. I can solve it now. I'm going to solve for x, and x will be in what unit? Feet. All right, so let's see, that'll be 1.75x equals 38.5. That's what 7 times 5.5 is. And then you divide both sides by 1.75. Anybody got an answer yet? 22. So the perimeter of the balcony is 22 feet. Questions? All right, that last problem is a little more difficult, and that's kind of even a difficult problem for that kind of problem. Going from a blueprint to an actual thing is a little more difficult than seeing two figures side by side. One of them you can add up and get the perimeter, the other one you got to figure it out. Here's your assignment. On page 468, do 1 through 7, 9 through 25 odd, 16 and 22, so you got to go back and pick up two even ones, 27 through 45, and 56 through 59.